All right, welcome back, everybody. Hopefully you had lots of coffee. Can everyone hear me okay? Okay, so this has all been building up to discussing how machine learning and data-driven optimization can be used in the field of fluid mechanics. This is why we're all here, okay? This is very rapidly changing. People in this room are redefining the art of what is possible every day. So, this will be different in a month. I don't need to convince you that fluid mechanics are important. Okay, we're all here because fluids are awesome. I was a mathematician before, and I drink a lot of fluids and I eat soups and I live inside of a fluid. And I remember I was looking at a bowl of miso soup, and I thought to myself, this is so much more interesting than what I'm studying right now. Fluids are amazing. They have patterns that are beautiful and useful, okay? This is a picture from a review paper Bernd and I wrote a couple of years ago on flow control. And if you don't need more motivation, we literally work and live inside of a working fluid. All of our machines do. Pretty much many trillion-dollar industries have a working fluid at the heart. And better ability to model, predict, control, and optimize fluids, even small improvements, percentage point improvements, would have a tremendous impact in enabling future technologies in energy, in transportation, and health. Okay? And again, I sound like a drum that's broken. All of our tasks are optimization tasks. Everything you've been working your whole life towards is an optimization that's high-dimensional, non-convex, multi-scale, and nonlinear. Okay, those are the problems we have. And that is the set of emerging techniques that is growing out of machine learning, is optimization-based models from data. Okay, good. So we wrote a review paper, Bernd and Petros Koumoutsakis and myself recently, on machine learning for fluids. So a lot of what I'm going to talk about is going to follow kind of this discussion. And I'm going to have some material from kind of all three of us in here. This is just a really pithy schematic of kind of how we see things working together in this kind of fluids data. There are the classical fields of theory, computations, and experiments. And now there's this fourth paradigm of data-driven inquiry. We now have data generated, vast amounts of data from these experiments and simulations. And in some sense, machine learning is a common data processing architecture that can kind of unify these classical modes of interacting with fluids. And this actually just goes to show you how I'm not that much of an engineer in a daily life. The first time I made this diagram, the gears didn't turn. And so I had to put in this little gear in the middle. Okay, so we're going to follow this basic progression. And actually, the way that this review started was in independent discussions with Bernd and with Petros. I heard this really interesting history of how machine learning, some of these ideas of evolutionary algorithms and genetic algorithms, came out of fluids dynamics labs in Berlin in the 60s and 70s. So Reichenberg and Schweifel, there were these great experiments where they were trying to, in this case, minimize the drag on a 5-section plate. So you could change the angles of this plate to change the lift and the drag. And they basically developed a crude version of a stochastic gradient descent algorithm to optimize the system through an iterative kind of evolutionary procedure. And I'm going to kind of butcher the history a little bit, so good thing Bernd's here. But the idea was, at the time, even though this was groundbreaking research at the time, this was kind of laughed at by the establishment. This was not fluid mechanics. This was not what this institute was all about. And it's only by kind of good luck and the support of others that they weren't run out of their institute. Yeah, Bernd's going to fill in.
So the reward for Rechenberg was he was thrown out of the institute. So he was 3 years unemployed in the institute of Rudibert King, because before Manfred Eigen, so a Nobel Prize laureate, rescued him, and then he was promoted immediately to a professor from being unemployed. and Schwefel was also thrown out of the institute. So both were accused of not doing fluid mechanics. Yeah.
So this is how this review came about, was kind of just, discussing with Bernd and with Petros this rich history that machine learning and fluid mechanics have grown up together. Kolmogorov is one of the founders of statistical learning, which is a major branch of machine learning research. We are one of the original big data fields. A lot of the modern computational architectures, data processing architectures, and algorithms were developed to solve fluids problems. So a lot of the advances in principal components analysis, how we compute the singular value decomposition. Sirovich in 1987 wrote the snapshot POD paper that changed how we compute proper orthogonal decomposition. In the same year, he showed that you could apply this to images of human faces, and he invented the eigenfaces algorithm. So that launched these two massive initiatives, but this was based on advances in fluids data. Another thing that's kind of interesting is this AI winter. So those of you who are students of history will know that artificial intelligence and machine learning is not new. And in fact, this had been there have been hype cycles before. And the AI winter in 1974 was largely due to the great fluid mechanician, Sir Lighthill, who essentially held 3 computer scientists and statisticians on trial. This is the trial of machine learning or artificial intelligence, and he essentially eviscerated them. They massively had overpromised and under-delivered, and Sir Lighthill, was largely responsible for the funding being cut for a decade in artificial intelligence. What's interesting is that one of his main points was the failure of human speech recognition, and you see this is auto-translated in Google right now. So it's kind of funny that a lot has changed, but some of his original points are still quite valid. You have to be careful about the hype cycle and not over-promising, but you also have to be, respectful of limitations of the time are not always going to be limitations. Okay, so really interesting and rich history. So in this lecture, I'm going to go through a couple of different aspects. I'm going to talk in general about what makes fluids interesting from a data perspective and challenging, and what are some of the challenges in machine learning. So I'm just going to talk about the incompressible Navier-Stokes equations. We have a Reynolds number. This is essentially how we get our complexity, is by modifying the Reynolds number. I love this picture from the Feynman book, just showing as you crank up the Reynolds number all of the kind of rich behavior that you get in your system. And again, Bernd's point is excellent that if I have one experiment or simulation, I have a tremendous amount of data, but I might only have that at a very small handful of cases here. So, for example, Feynman distilled these 5 Reynolds numbers as being the pillars that you can interpolate between or extrapolate through, however you want to think about this. But that's only 5 kind of data points in that dimension. Okay, that's not enough for neural networks to really learn based on. And you have a really interesting set of phenomenology. This is just the drag coefficient as you go through the Reynolds number. This is actually why those ball drop experiments don't work, is because the constant gravity argument is not really sufficient. You have this massively velocity dependent drag profile. It's extremely nonlinear. It's not a constant. Okay. Good. This is a picture that I got from Sam Tyra from UCLA. I love this this picture of our Reynolds number 100 flow past the cylinder. This is our favorite benchmark. And then this is a satellite image of the flow over Rishiri Island in Japan. So even though you have this extreme complexity in your fluid systems, this massive range of scales, oftentimes you still have these dominant patterns that emerge that actually look relatively simple and low dimensional. So pattern extraction is one of the key areas of machine learning research in fluid mechanics, and then modeling how those patterns evolve. And in fluid systems, I remember hearing this from Lex Smits, who basically said you can tell a low budget movie by how many scales their turbulent explosions have. And so that's one of the hallmarks, is that anytime you zoom in, you get this kind of self-similar structure, and maybe self-similar is an abuse. You have, every time you zoom in, there is more structure to look at in these highly turbulent flows. And that makes them very challenging to model and to simulate, because sometimes these little scales, maybe they don't matter instantaneously, but their bulk effect does matter. Okay, so we have really rich planetary data. So this is a simulated satellite image from the Gulf of Mexico. So this is a really, really rich fluid flow. I think we have decades of this collected every hour over the entire globe. This is a tiny, tiny fraction of the data we have. This is the Ocean Next project. This is an incredibly large circulation model that the Europeans have been developing and trying to model kind of these fluid dynamics over large time scales. And this is just a set of videos I picked out to show. We had an IPAM workshop, a 3-month workshop on machine learning for physics. And these are just videos I decided to show a bunch of non-fluids people to get them excited. I love this one. Right, you see kind of just this massive range of scales and complexity in this Rayleigh-Benard convection. And this will just keep going. This is like a 5-minute video, and it only gets better. Yeah, question in the back? How can you tell what a fluid is doing from a satellite image? Oof, okay, good question. So, so the measurement is not my strong suit. I'm assuming they measure something and then they infer something. I know that around airports you can use LiDAR to measure things. I know people use radar, Doppler, velocimetry. Yeah, measuring ocean currents is actually still a pretty big problem. A lot of people drop buoys in the ocean or drifters and floaters. It's expensive. So you're constantly assimilating data from different sources, satellites, and on passive and active tracers and robots on the ocean. So a lot of data streams for assimilating this, but that's not I'm sure other people know better than I do. Isn't that great? I mean, really interesting. You should download this video. I'll make all the slides available. This is a fun one from the KTH group that's been inspiring a lot of work for quite some time, is just trying to understand kind of this rich multi-scale behavior in these boundary layer simulations. So this is, you can see these hairpin head vortices forming in this long developing boundary layer. And this just gives you some of the idea of the complexity and scale at work in some of these problems. And we're probably still decades away with Moore's law from simulating flows at industrially relevant Reynolds numbers, even with the biggest supercomputers, let alone being able to simulate them in real time or multiple, an ensemble of simulations for design optimization and control. Okay, so getting reduced representations of what's happening here, the things that, that matter for an engineering objective, is extremely important and extremely challenging. I mean, this is just so cool. Okay, I've always been inspired by this set of quotes from the Feynman lectures. This is kind of, I think, a really profound view on fluid mechanics. It's a lot of text, I apologize. But the basic idea is that, when you have a new situation, you try to make analogies to an old situation you've seen before. And he makes some comments about fluids. Have you never visited the Earth? Could you predict the thunderstorms, the volcanoes, the ocean waves, the auroras, and the colorful sunset? The basic idea here being, yes, we have governing equations. Yes, we know Maxwell's equations and Navier-Stokes equations. You would never predict thunderstorms from those equations, just if you had those equations. Okay, and there's this huge conceptual gap between having equations and having understanding or knowing what is possible. Okay, and that's something we struggle with. We don't know how effective of a flow controller we could possibly design. Like there's no theory for what the upper limits are in some of these situations. And so he says the next great era of awakening of human intellect may well produce a method to understand the qualitative content of equations. And I think this is really important. We get stuck often on this idea that we have the equation so we understand everything. And that's certainly not true. Okay? We don't believe that's how a moth interacts with a fluid, through equations. Okay? Good. And so how do we study flows? And this is, again, this is how we are going to be studying them with machine learning. We study them through canonical flows. We find simplified examples and analogies. We work through analogies, and that's how our machine learning is going to develop. You're going to be developing models for different scenarios. Okay, so there's all kinds of cool examples. You have bluff body flows and wakes, which has one type of behavior and physics. You have mixing layers and shear flows. That is a whole, kind of different can of worms when you're modeling, right? So, for example, run DMD on flow past a cylinder and a spatially evolving mixing layer, and you'll find very different challenges in this modeling procedure. Yeah, and then all kinds of other problems. So one of the big ones is acoustic noise generation and turbulence and shock waves. And, scramjets are really important. We want supersonic transportation, hypersonics. And currently our models are too slow to really be useful. So we build experiments and we run these massive simulations. We need to accelerate these. Okay. Remember, the big change in machine learning in the last 10-ish years started with a data set. Okay, it did not start with a neural network. It started with a massive data set. This was essentially a service that someone did. They had the vision that this was what was needed, and they put tremendous resources into generating this library. And so that is the only way we as a community are going to move forward in machine learning research for fluids, is to have canonical, agreed upon benchmark problems and data sets. So for example, Bernd and team have been working on the fluidic pinball, which you've probably seen, the 3 cylinders. That is one new benchmark problem that has additional complexity that people can work with. There's some great ones out there. The Johns Hopkins database has really been pretty useful. I mean, how many of you have used the Johns Hopkins database? A lot of us. Very useful. This was not designed with machine learning in mind, I don't believe. Right? This is a bit older, and so there are some modifications that are going to be necessary for this to be useful for things like closure modeling and some of the modern tasks. Flow control. You can't just do flow control on a static data set that you download off the internet. Okay, you need a simulation or an experiment. But this is a commendable effort. This is where we need to be working, is to have agreed upon benchmark problems that we can compete our algorithms on. Okay. Yeah, this is just one example from this kind of turbulence data set. Is you see these kind of scales within scales of vorticity. So every time you zoom in, you kind of see additional scales. This is probably the Q criterion. I'm not entirely sure what's being plotted here, but I'm guessing it's Q criterion. And when you zoom in, you can see kind of additional structures. So, I mean, this is not a toy data set. This is not flow past a cylinder at Reynolds number 100. This is much more sophisticated multi-scale fluids data. Okay, but this is a challenge. I mean, someone in this room hopefully is going to be developing the next kind of version of this that we can all use. We should be doing this together. Okay, I'm going to talk about some interesting examples of machine learning in fluid mechanics, and this is going to be highly biased to work that we've done and work by collaborators. So I'm just going to tell you our perspective. And the idea is not at all to be thorough or comprehensive, because that would be impossible. I just want to give you a flavor for some of the cool things you can do. Okay, so machine learning is just optimization with data. So I'm going to start off with something that has nothing to do with neural networks. Okay, because I think that's healthy for us all. I'm going to talk about the robust proper orthogonal decomposition. This is work by Isabel Scherl. So she has a poster outside, and you should talk to her about this. and it's really, really interesting. So we all are familiar with the POD. We use it all the time. How many of you have done POD on experimental data? Okay, are your experiments clean? I mean, probably you hope so, but like, do you have Gaussian white noise on your experiment? Do you have outliers and corruption? Every experimental data set has outliers and corruption. It looks like TV static on top of a flow field. Okay, even the good ones, yeah. Same is true for CFD. And so we had this idea, there are really powerful techniques from statistics to robustify these algorithms. And these are really simple modifications to our classic algorithms. So of course we know about our POD, we can decompose a very high dimensional flow field into a linear subspace spanned by a small set of orthogonal modes. That's very useful for taking something that was large and intractable and bringing it down to a representation that's finite and manageable. You can build models here and do control and all kinds of stuff. But when you have experimental data, you often get corruption that messes up your modes, okay? And so there's this really cool algorithm, Candes et al. And others in the field of robust statistics have been developing these algorithms over the last 10 years, maybe 20 years. This one is called robust principal components analysis. And remember, anytime I say PCA, you should be thinking POD, they're basically the same thing. So this is the Yale B data set, where you have 36 individual human faces, and for every single human face, you have 64 images of that person with different lighting conditions. It's a really cool experiment. They built a geodesic dome with a bunch of lights and a camera, and they just flash them in 2 seconds and take 64 images, so you get all the shadows. Okay? And so with this massive data set, what you can do is you can learn what are the statistical features of a human face. Like, we're not as different as we think. We all are an oval with some circles and some dots, right? Like, we're basically the same. And so once you learn the statistical features of what makes up a human face, this is literally just doing POD on a library of human faces, you can use that statistical knowledge of what makes up a human face to subtract off large occlusions or outliers or corruption. So you can put a mask on this person, this funny mustache, and the algorithm can say, based on what I can see in the algorithm, this is consistent with the low rank dynamics, with the low dimensional dynamics observed in the data, and this is all of the stuff that is an outlier, a sparse set of outliers. You can literally like pull a disguise off of someone. You can't rob a bank with a hoodie anymore, because if any part of you is showing, they're gonna correlate it and figure out what your face looks like, okay? So the idea here is you can use this for corrupt flow field data. This is, I'm going a little fast. Does this make sense what I'm saying? There's statistical features in the data. This is not random data. These are human faces. And so even if I see a human face with something messed up, I can figure out what's under that based on the statistical correlations with what we have in the database. Now, again, this is an optimization problem. I haven't shown you how you solve for L plus S. This is a non-unique problem. There are many L's and S's that add up to X, right? This is a massively underdetermined problem. There's infinitely many solutions to splitting X into L plus S. So you have to set up an optimization problem so that the solution you want is the one that comes out, okay? And this is the solution that you would, this is the optimization problem you would want to write down. You want to write down X is split into these two matrices such that the rank of the low rank part, the number of POD modes is minimized, and so that the L0 norm of the sparse corruption part is minimized so that there's as few kind of outliers as possible. But this is a non-convex optimization. This can't be solved in polynomial time, so you relax it. And that's a huge theme in machine learning, is you add these penalties to promote unique solutions in underdetermined problems. Closure modeling, it's an underdetermined problem. What is the prior, what is the regularization you're going to add to pull out the solution that is most physical? Okay, and in this case, sparsity tends to be a good regularizer for corruption and robustness. And so this is the convex relaxation that Candes came up with. Isabel has applied this to lots of interesting flow data. So this is our favorite Reynolds number 100 cylinder that we've massively corrupted with salt and pepper noise. I mean, this is real. This is a real movie from the method working. Okay, so you run this movie, you build a statistical kind of understanding of what a flow field is, what the low dimensional structure of a flow field is, and when you run it through this optimization, what comes out is a very clean low rank structure. You can see that there is a little bit of a shadow of the noise in the wake, so this is, we're not cheating here, this is really data, and all of the outliers got pulled out. Okay, so you can do pretty amazing things with, yeah, question in the back.
Can you wait that
Just 1 second.
So the S matrix, it's sparse in what sense?
Sparse literally means it has mostly 0 entries. It is only a few non-zero entries.
But like,
yeah, it doesn't
seems
look
like the
that
noise
sparse.
is
It's a
everywhere.
little hard to see. I think this is probably about 20% corruption, but we're computing vorticity from it, so it corrupts its neighbors too. So it's a little hard to quantify, but sparse just means you want it to have as many 0 entries as possible. It doesn't mean it has to be 1%. It could be 30%.
So is in general noise usually sparse or localized in certain regions of the flow?
So this is really important. If we had contaminated our data with white noise everywhere, regular POD would have been optimal for filtering that. If I had enough data, the SVD is the best thing you can do to filter white noise. Okay? That's like how it was developed. Principal components filters white noise, Gaussian noise, okay? This is not white noise. This is salt and pepper corruption. You like manually take the pixels and make them +10 or -10 at random. Okay, so this is more like the kind of corruption you see in experiments from PIV imaging. You could also do something like you could have this movie and then one of the frames, the back part could have just been blacked out. And what that does when you do a POD is a linear regression, and that's going to tilt the whole regression plane because of that one outlier. And this will robustify it and get the modes back. Okay, good. And so this, these are the true modes from the clean data. This is what you would do if you ran POD, just vanilla POD on this contaminated data. And this is Isabel's robust set of modes. So you get a massive cleaning of this. And we only have a few periods of this data. I think we have 5 periods of shedding, something like that, 2 periods. You can use these modes to build models. And when you do DMD before, these white circles are kind of the truth. And you get this terribly contaminated model here. And after RPCA, you almost nail the correct eigenvalues here. You can actually quantify how much noise reduction there is based on this really nice work by Shervin Bagari, who quantified kind of how noise would mess up these eigenvalues. So that's, I think, a really cool connection to some classical theory of Koopman and DMD. And so Isabel applied this, if we had just applied this to our toy data set, it would be cute. Isabel applied it to 2 experimental data sets that are actually of interest to us and are actually corrupt. This one is data from Jessica Shang's PhD work. This is flow past a cylinder at Reynolds number 413. This is more like what I'm used to seeing, right? It's pretty noisy. It looks like there's a lot of TV static on top. And it's not Gaussian white noise. You see these like bright spots just kind of flare up at random. Those are occlusions and outliers. And so when you run through this optimization, and this is something interesting, that regularization term, that L0 term that we added to make our solution unique, you get to decide how much to weight that term. And that's, again, just like in the Cindy algorithm, you have to choose how important sparsity versus accuracy is to you to find the right solution. The Candes paper has a guideline for how to choose lambda, given some assumptions, and it turns out to be a pretty good assumption. So if we have lambda too small, we overfilter, and a lot of the coherence goes into the sparse part. So this is overfiltering. If the lambda is too high, we are not being aggressive enough, and we are catching some of the massive outliers, but this is still pretty crummy. And so there's this Goldilocks zone in the middle where you get kind of just the right amount of lambda, and it's inevitable that you're going to filter some structure and you're still going to have some contamination because this is real data, but this is still significantly cleaner. I mean, look at the difference. This is what you want. And it's a little subjective. You have to make a judgment call about about what you want. So we've also applied this to the Johns Hopkins turbulence database, actually, where it is multi-scale, and we know the truth of all of the scales. And Isabel carefully quantified, as you change this lambda, how do high-frequency structures get filtered. Okay, so you can really use this algorithm right now. Question there? Yep.